Hi, everyone. Welcome and good evening. My name is Benjamin Quinn, and on behalf of Harvard Bookstore, the Harvard University Division of Science, and the Harvard Library, I'm excited to introduce this virtual event with Arik Kershenbaum, presenting his book, The Zoologist's Guide to the Galaxy, What Animals on Earth Reveal About Aliens and Ourselves, in conversation with Lewis Gross. I hope you're all well and safe. Thank you for joining us virtually. This evening's event is the latest installment in our Harvard Science Book Talk series, which works to bring the authors of recently published science literature to our Cambridge community and beyond. In just a few days, on Tuesday, April 19th, we'll host renowned primatologist Frans de Waal for a presentation of his latest book, Different: Gender Through the Eyes of a Primatologist. To learn more about this and our other upcoming virtual events, you can visit harvard.com and sign up for our email newsletter, or check out the page harvard.com/science for more info. I'll also be posting a link to our Science Research Public Lectures channel in the chat, where you can view previous talks you might have missed. This evening's discussion will conclude with some time for your questions. If you have a question for our authors at any time during the talk tonight, click on the Q&A button at the bottom of the screen, and we'll get through as many as time allows. In the chat, I'll be posting a link to purchase the Zoologist's Guide to the Galaxy on harvard.com. Your purchases and financial contributions make events like tonight's possible and help ensure the future of a landmark independent bookstore. Thank you to our partners at Harvard University, and thank you all for showing up and tuning in support of authors, publishers, indie bookselling, and especially for science. And finally, as you may have no doubt experienced in virtual gatherings, technical issues may arise. If they do, we'll do our best to resolve them as quickly as possible. Thank you for your patience and understanding. Now, it is my sincere pleasure to introduce tonight's speakers. Dr. Arik Kershenbaum is a zoologist, college lecturer, and fellow at Girton College, University of Cambridge. He has done extensive fieldwork on animal communication, following wolves around Yellowstone National Park, decoding the whistles of dolphins among the coral reefs of the Red Sea, and the songs of hyraxes in the Galilee. He is a member of the International Board of Advisors for METI.org, a think tank on the topic of messaging extraterrestrial intelligence. Today, he is joined in conversation by Dr. Lewis Gross, Chancellor's Professor in the Alvin and Sally Beaman Distinguished Professor of Ecology and Evolutionary Biology in Mathematics at the University of Tennessee, Knoxville. For almost 3 decades, his research and education efforts have been continuously supported by awards from the National Science Foundation, and he has served in leadership roles in the National Institute for Mathematical and Biological Synthesis, the Ecological Society of America, and the Society for Mathematical Biology. This evening, Arik and Lewis have joined us for a discussion of The Zoologist's Guide to the Galaxy, a wildly fun and informative investigation of life in the outer reaches of space, which Philip Ball, author of Nature's Patterns, calls an entertaining, eye-opening, and above all, a hopeful view of what, or who, might be out there in the cosmos. Though scientists remain confident that life exists elsewhere in the universe, our understanding of this life remains the stuff of science fiction. Using his own expert understanding of life on Earth and Darwin's theory of evolution, which applies throughout the universe, Arik Kershenbaum gives us one of the first guides to what alien life must be like, how these undiscovered creatures must move, socialize, and communicate. I will end with high praise from Lewis Dartnell, who writes, surveying the deep time of evolution on Earth and his own cutting-edge research into animal communication, Kershenbaum provides a fascinating insight into the deepest of questions. What might an alien actually look like? We've got a lot to learn this evening, so without further ado, I am delighted to turn things over to our speakers. The digital podium is all yours, Arik and Lewis.
Okay, fantastic. Well, excuse me, I'm getting over COVID, but I'm going to talk for a few minutes. I will give a brief introduction to the sort of stuff that I talk about in my book, and then Lou and I are going to have a bit of a chat and answer some of your questions as well. So really, I'm going to ask a question that you might think is a question that can't be answered. What is alien life like? But it's a question we've got to start asking. It's a question that the time to ask this question has come. We are on the verge of discovering life outside of the planet Earth. And we've got to get away from all the science fiction and all the conspiracy theories and get down to thinking about what this life might actually be like, and using the evidence and the information that we have from Earth to make conclusions about the possibilities of alien life. Now, you might say, we've never seen it, so we can't actually make any conclusions. But that's not true. And I hope I'm going to be able to convince you that that's not true. In the same way we study the laws of physics on Earth, and that tells us about how stars work in distant galaxies, so we can study life on Earth, and that will tell us a lot about how life can work on other planets as well. So for those of you who remember back in the 1980s, before we discovered there were even planets around other stars, everyone was very skeptical about the possibility of life outside of Earth. We didn't really know what was out there. But then as instruments began to be developed that could detect planets around other stars, it became clear that there were places where life might exist. Now, the first planets that were discovered obviously were very large, and these hot Jupiter planets are not really very hospitable places. But as the instruments improved and techniques improved, we discovered more and more and more and more planets, including many that were very much like Earth, rocky planets, for instance. And a recent estimate is that there are somewhere between 11 and 40 billion Earth-like planets in our galaxy. Not just planets, Earth-like planets in our galaxy. That is a lot of places where life might exist. And now we're developing even newer technologies. So the James Webb Space Telescope, for instance, is going to be able to peer into the atmospheres of these planets and look as the light comes through from the star that they're orbiting, and detect changes in the spectra of the light as it passes through this very thin layer of atmosphere, and look for chemicals that may indicate that life exists. Maybe oxygen, maybe industrial pollutants, for all we know. And so we're quite confident that some indication of life somewhere in the galaxy will be forthcoming relatively soon. Of course, if we detect oxygen or something else in one of these atmospheres, it won't tell us anything about what these aliens look like. And for that, up until now, we've had to rely on science fiction. And science fiction has loads of ideas about what alien life might look like. And interestingly, although people make fun of science fiction aliens for being basically humans with makeup, but what I find interesting and disappointing about science fiction aliens is that they're always portrayed as complete organisms. They are the way they are because they should be that way. But that's not the way that biology works. Organisms evolve slowly, step by step, from simple beginnings, with an advantage at each step, and become more and more suited to the niche that they occupy. So we've got to stop thinking about aliens as being complete beings, complete organisms that have all these particular facilities, and think about where they might have come from, what they might have evolved from. Of course, everything evolved from simple beginnings. If we think about life on Earth, so life's been around for a very long time on Earth. The Earth's about 4.5 billion years old. Life's been around probably for 3.8 billion years. Pretty much as soon as the habitat on Earth was suitable for life arose. But for most of that time, life has been very, very, very simple. Basically, it's been slime. Organisms that look like the sorts of things we would call animals really only evolved 500 million years ago. All of the rest of this time, life was really relatively simple. Some strange things happened on Earth, right? The whole planet froze over from pole to pole at least twice during this period. So what exactly happened during that long period of simple life on Earth? And why do we think that the same things that happened in those 3 billion years here on Earth would have happened on other planets as well? Maybe different things happen on other planets, and therefore we can't really say very much about what life is going to be like. But of course, I think that we can. And my book goes into some detail, some information on the kinds of things we can say about alien life. We can talk about the way it moves. We can talk about the way it communicates. We can talk about what kind of intelligence alien life might have. I'm not going to have time to go into all of these things, but I'm going to give a very, very brief idea of the kind of reasoning that I'm using. The reason that I say we can say a lot about what alien life is like is because life is fundamentally constrained. Not everything is possible. And so solutions that are possible will occur again and again and again on Earth and on other planets as well. If you think about movement, for instance, well, movement is a very simple process of mechanics. If you need to exert a force, so you need some friction, but you don't want too much friction because it slows you down. And so legs are just a brilliant invention. They're a solution to moving on a solid surface. They're not an Earth solution. They're a mechanical solution that will apply on other planets as well. And once you're moving, if you think about it, if you've got a front and a back, you also have a left and a right. And symmetry is something that is so ubiquitous on Earth. Almost all animals on Earth have this symmetry down the middle, a left and a right side. It's so useful. It makes movement so much more efficient. Again, that's nothing to do with Earth. This is something we can expect to see on other planets as well. And another excellent example of the constraints on life is in flight. So we know that flight evolved on Earth 4 times with birds and bats and insects and pterosaurs. And in every case, they had wings. Completely different wings, of course. You know, bats have got these long fingers with skin between their fingers, and insects have got their wings sprouting out of their cuticles, but they're wings nonetheless. And that's because there's just not that many different ways to fly. If you think about it, we only really know 3 different ways to fly. There's ballistic flight. You can jump and launch yourself into the air. That's not very controlled. There's buoyant flight. And of course, fish fly through a fluid without falling to the ground. But flying through a liquid is quite a bit easier than flying through air. And if you want to fly through air, really, the solution is to go with wings. Again, this is not an Earth solution. This is simply a mechanical solution. Now, apart from mechanics, there are also constraints that are actually mathematical. They're actually fundamental to the way that organisms interact. And these are ideas that are based on things like game theory. So just to give you a very sort of brief introduction to the sorts of things that we can be confident will apply on other planets. If you think about what's called the hawk-dove game, so you imagine a population of doves. They're all really friendly and they're nice, and they're all being really nice to each other. Everyone's having a great time. Along comes a hawk. Now the hawk is going to be ruthless, is going to exploit the doves, and very soon going to be much more successful, and the hawks are going to start taking over from the doves. But a society of hawks is a pretty nasty place to live. They're all fighting with each other. They're all competing. It was much nicer when everyone were all doves. And so it's possible that a few doves could still eke out a bit of an existence amongst these hawks. And these kinds of interactions have nothing to do with the way that life has evolved on Earth. These arise purely from understanding the interactions between individuals and individuals competing with each other. Now, of course, the main thing that we use when we think about what alien life might be like is the fact that all life, everywhere in the universe, shares a common mechanism. Every life must have evolved through natural selection. It's the only way that complexity can accumulate. And the whole point about life is it's incredibly, incredibly complex. You've got to remember, although we all understand how bacteria, ancient bacteria were very simple, and then more complex life evolved, and eventually animals and so on. But even the earliest life, even those ancient bacteria, are unbelievably complex. And somehow for a soup of chemicals to turn into these complex bacteria, it can't have happened by chance. This could only be through evolution by natural selection. So this is the one principle that we know really will apply throughout the universe. Now, although we do understand what evolution is and how it works, we are learning more and more all the time. And there are a lot of subtleties to evolution by natural selection that perhaps weren't so apparent a few decades ago. And one of the things that's very interesting is that the very earliest life that existed on Earth probably lived in communities. So this, what you see here on the left, is a fossil stromatolites. This is one of the oldest fossils of life that there is. It's about 3.5 billion years old. And you can see at the bottom, modern stromatolites. So these are mats of cyanobacteria, of blue-green algae, and they're growing together. They're growing in layers and growing on top of each other, growing out of the water like that. And we see in bacterial biofilms that exist at the moment, even something as small as bacteria, even something as simple as that, lives in communities, communicating, sharing information, sharing resources, competing. These complex interactions have been going on since life began on Earth. And it's the nature of complex interactions that really modifies the way that evolution works. Social groups, communities, solve an awful lot of problems. Problems about how to get resources, how to protect your resources against others who are competing for them, how to prevent yourself from becoming someone else's resource, for instance, from being eaten. These are all common problems to organisms that live in large numbers, and they're often solved by living in communities, by living in groups. Social living has evolved many, many times on Earth, and not because it's Earth. It's evolved because it is such an incredibly useful way to live. It's almost inevitable on a planet that has anything resembling what we would call animals. But it's not all roses. Living in societies is difficult. It's true, you're cooperating with members of your group, but you're also competing with them. And that competition can get quite complex. There can be a lot of interactions. There are dominance relationships, there's exploitation and deceit and so on. And what we see on Earth is that when animals live in complex societies, then they have to evolve intelligence. Intelligence evolves as a response to complex relationships within a society. And that's something that we can expect on other planets as well. So just wrapping up before we get into a discussion, what's alien life going to be like? I didn't really talk about all of these, but it's all in my book. All life needs energy. We know that for sure. All life needs energy. There are many sources of energy. The sun or the star is not the only one, but it's likely to be one that's very common and very widespread and found on most planets. There are places where life may exist, for instance, in an underground ocean, and then perhaps photosynthesis might not occur, but some form of energy must be used. Once you gather energy, someone's going to come and take it from you. Someone is going to come and try and steal your energy from you. And that's predation. Predation is almost inevitable. It's almost inevitable that predation will arise. Once there is predation, then there is value to running away and running after your food, of course. So movement and efficient movement depends on symmetry and also in many cases legs. Haven't talked at all about sex. We could talk about that a little bit. We don't really know what alien sex will be like, but there are reasons to think that sex of some form is probably important. And following on from that and from what I was saying about communities, family groups are going to arise as well. And then once you have large groups living together, then you have intelligence, then you have communication, and then hopefully, possibly, also technology. So that's my whistle stop tour. I will stop sharing my screen, and yeah, we can have a bit of a chat.
Thank you so much, Arik. That was a magnificent quick summary of a wonderful book that hopefully opens lots of people's eyes to a very different approach to thinking about science fiction and thinking about life on this planet and what we can learn from it. So I'd like to kick this off with noting that you mention any number of science fiction books and people in the book in various contexts. I want to put you on the spot and say, who got something right from your perspective as an evolutionary biologist, and who really got something wrong? And you don't have to mention names if you don't want to, but.
Well, so first of all, disclaimer, okay, science fiction isn't only about predicting science, right? That's not actually what the role of science fiction necessarily is. It's about putting up a mirror to ourselves, a distorted mirror. So there's all kinds of things that science fiction can do. And I just love the idea of Spock as struggling with logic and emotion. Okay, this is not what we think aliens are like, this is what we think we're like. But to answer your question, well, who got it wrong is quite a famous answer to that. So one of my famous science fiction stories is The Black Cloud by Fred Hoyle. Fantastic. I mean, it's a wonderful book. It's a great book about science, about how science is done. And it's really very clever and very innovative. And Richard Dawkins was totally furious with this book, which was written in the 50s, but nonetheless, he wrote a very scathing introduction to a recent edition because the evolutionary biology is just completely wrong. And the reason it's wrong is that the story postulates this solitary, intelligent cloud of gas floating through the universe. Now, okay, Fred Hoyle believed the universe had always existed and has been existing for an infinite time. So perhaps evolutionary considerations weren't at the top of his agenda. But still, the question has to be asked, why would a solitary cloud of gas be intelligent? There's no adaptive advantage to that intelligence. It doesn't serve any purpose. Things don't become intelligent just because it makes a good book. So I think that's an example of where where it went wrong. Science fiction that went right. There's a lot. I do like Robert Sawyer's a lot of his books and books that look at. So there's I don't know, pull one off the shelf. Calculating God, for instance. Story about an alien comes to Earth. Why? Because they're looking for God. Right, so they're going through other planets. They haven't solved the mysteries of the universe. So, well, let's go around and see if other civilizations have solved the mysteries of the universe. And I think it's, yeah, I mean, I think it makes sense that difficult questions aren't going to be solved easily by even by a highly intelligent civilization.
Okay, great. I really appreciate that. Comment and I'd like to ask about the Black Cloud in particular, because of course there is a whole deal of astronomy that looks at regions that are interstellar gas clouds, and they have within them all the precursors to life. And in fact, there have been papers published about essentially the use of these to seed life in other places. So I wonder if you might say something about the possibility for seeding life, which is again a theme of much of science fiction, and whether that's even possible from an evolutionary perspective of thinking about what you could put on a different planet that might then lead to something like intelligent life eventually. And again, this is a theme of science fiction. Is that even possible? I mean, well, plausible, let's put it that way.
Well, one thing that I think is important to say at the beginning is that these compounds well, let's start with water, right? Water's unbelievably common in the universe. I mean, it's incredibly common. Water is not rare. There's no coincidence people look for water as a useful solvent for life. It's because it's just everywhere. but even amino acids are pretty common. It's true that it's surprising, and you do look and say, oh wow, there are these interesting organic compounds in these clouds, and that is interesting, but it's not all that rare. So these are still relatively simple compounds. So I don't think we need to be overly excited about that. Could they seed life on planets? Of course they could, and we're still such a long way from understanding how complex life or how life could have evolved on Earth. That it's very, very hard to know whether these compounds could have been formed on the surface of the Earth, or whether they really had to come from outside. Mostly, I think, though, I think that amino acids, simple compounds, they can be formed fairly easily on a planet's surface. It's getting them to get together and make these reproducing molecules is really the tough part. And if you did want to seed a planet, let's say we wanted to go out and seed life on other planets, then probably the best place to kickstart would be to put those reproducing molecules, because at the moment we just don't know how that could have happened. We don't really have an answer to that.
That's great. So as a sort of follow on to this, you noted that, you know, there are a lot of planets, presumably in our galaxy, let alone elsewhere. And there were calculations, of course, by many people involved in sort of the search for extraterrestrial intelligence ideas early on, about how many of those planets might be habitable in the sense of being able to support life like ours. But also that timeline that you put up indicated that the vast majority of time on the one sample point that we have, us, has not been even animals, let alone intelligence or anything like intelligence. So it means that even though there might be billions of potential planets, the time periods under which intelligent life might form is probably pretty small. So what you focus very much on animals and a very little bit on plants. And so I'm going to ask you, if you were to write a book about evolution and sort of the autotrophic aspects of life, the generating energy aspects and not feeding on others, what might be different in the underlying ideas of evolution that you used, if anything?
And perhaps less than you think. So, I mean, you're not really talking about plants. You're talking about autotrophs, because,
yes,
of course, you know, all that huge period of time, these were not plants. And what's more, there were plenty of heterotrophs around at the time as well. So we know that they're single-celled amoeba, basically, that, you know, were crawling over these blue-green algae and munching on them. So there were ways of taking your energy from others even before there were animals. But we do have to think about what we mean by animals. Now, on Earth, it's easy. It's easy because all life on Earth has a common ancestor. So we just say, well, animals are all of those organisms that are descended from the common ancestor of all the animals. But that becomes a problem when we go to other planets, because we don't have that common ancestry. So we do need to think a little bit about what we mean by animal. Now, traditionally, before going over to that evolution, the phylogenetic definition, people defined animals as heterotrophs, so they get their energy from others, and they're also multicellular. Now, as I said, amoeba, just one cell, and they will eat other things. So does that make them? And if we found an amoeba on another planet, would we call it an animal? Well, I think I would. I'm not sure what the role of multicellularity is. This is a very difficult and complex question. Whether complex life must be multicellular. There are people who think it must, and people who think it needn't. But for me, what's really interesting about animals, and the reason, excuse me, that I focused on animals, is because animals have a characteristic that really brings in a lot of other evolutionary constraints, and that is they need to make time critical decisions. Okay, they are acting in a moving, a dynamic environment where other animals are coming to eat them, or the ones they want to eat are running away, and so that spawns a whole range of traits and characteristics that you wouldn't see if you didn't have that dynamic environment. Now, I'm not saying that plants are boring. Plants are fascinating, and plants do loads of really, really, really interesting things. But I did want to focus on those traits that arise as a result of the dynamic environment.
Okay, and I know that you make the argument that that dynamic environment really is necessary for the evolution of intelligence, that is really required for that. So I assume by that intelligent plants or intelligence in autotrophs may be possible, like Groot, and as you mentioned, in Gardens of the Galaxy, but that the way that we normally think of plants, it's probably not likely to see intelligence. Normally think of as in the common parlance.
I would actually turn that on its head, and I would say intelligence, as we normally think of it, you'd not be likely to see in plants. Now, right. Do plants have intelligence? Well, I mean, they do, in the sense, if we're just going to define intelligence in its broadest sense of solving problems, they grow towards the light, and that's a way of solving a problem. But I think that when we talk about intelligence, we are talking about this dynamic intelligence. We are talking about solving problems quickly because you have to. Mm-hmm. So I think that wouldn't evolve in plants that are like plants on Earth. You took the example of Groot, but Groot's got legs, right? He runs. So actually, as far as I'm concerned, he's an animal. He can photosynthesize, still an animal. But we can argue about that.
We can ask him, right? Ask his creator.
And Groot.
I wanted to, since we brought up Groot and movies, as we were talking before, you know that there is this field of zombie science, which applies ideas from science, including evolutionary biology and ecology, to issues of whether zombies could exist, and the whole feature associated with their characteristics in fiction. And I know that the people who've worked on this have actually been asked to be consultants on movies about zombies. And so my question is, have you been asked to be a consultant regarding intelligent life in any science fiction movies? And would you hope to do so? And what might you say to the people?
Well, I have, and I can't really say which ones, but usually when that happens, the first thing I say is what I said right at the beginning here is, right, we know science fiction is not meant to be realistic. Okay, you don't have to do this, and oftentimes the producers will come back and say, no, okay, we understand, but we still want to be the movie that is realistic, and that's fine, and I actually think that can be really appealing, and the place where it's sort of where you see that appeal is in the Avatar movie. So where they went to all this effort to build this huge ecosystem and all the different kinds of animals, and okay, they were Earth animals painted blue, but still the fact that those interactions were portrayed, I think is really important, because as I mentioned right at the beginning, you can't just say, okay, an alien, it looks like this or does this because that's a good thing for them to do. For it to be convincing, you need to see why they would have evolved that, why that was useful in the environment in which they live. So I think seeing the whole ecosystem picture does help.
Okay, and you do emphasize in the book the basically the adaptationist paradigm in which, the argument is what we see across the planet has been selected through processes of evolution to lead to organisms that are more able to survive and reproduce relative to those who do not have those particular traits, that sort of standard definition of selection. But you don't talk much about group selection. There's a lot about kin selection in there. And I don't know if we want to go there or not, but presumably as soon as there is group living and you make a good argument for cooperative behaviors to ameliorate the impacts of competition and that leading to the potential for intelligence. So what if any other aspects of evolutionary biology that you don't really emphasize in the book might be appropriate to think about? And again, I'm bringing this up because of the tremendous arguments about group selection in particular, and we should perhaps define that as not selection at the level of the individuals, but as arguments that groups that better are able to survive and reproduce pass on their group traits.
Yeah, I mean, it has been a hot argument, and I imagine that most of the viewers probably aren't particularly interested in these detailed arguments between scientists. But I think there are a couple of really important points. One is that okay, most modern evolutionary biologists would say that group selection on Earth doesn't really occur, and so that's in the sense of animals don't sacrifice themselves for the good of the group. Essentially, is what it comes down to. But there are reasons why we don't see that, and those reasons are quite specific. And in other circumstances, they might not apply. And evolution on other planets might be driven by such self-sacrificing and group selecting processes. I mean, there are little things that would need to be different. So it's as a process, it's not impossible. We don't see it on Earth. It's a good example of a process that we don't see on Earth that could potentially occur elsewhere. I think though, possibly the more interesting evolutionary process that I don't talk about that actually is quite important on Earth is what's called neutral selection. So although we tend to think that the characteristics that animals and plants and other organisms have are adaptive and they suit them well and they help them to survive well in the niche. In fact, a lot of traits that organisms have are kind of random, and there are reasons for that, which are to do with the way that species form and way that when populations get isolated, they just tend to sort of randomly become different, rather like accents become different. The fact that I have a different accent from you, there's nothing adaptive about that. It's just that two populations have been separated for a long time.
It might be if you wanted to attract a certain female, right?
Well, I mean, what happens then, of course, is that you have this within the group. There's a particular kind of mating behavior or accent or whatever that's deemed acceptable. That, of course, is one of the things that drives new species to form. But so I don't talk much about that. It's true, and the role of neutral selection, which is probably greater on Earth than we even realize at the moment. Yeah. Well,
since we're on this topic, I wanted to bring up altruistic behavior because, of course, a number of the science fiction books involve communication in which one, alien civilization helps us generally by transmitting information that allows us to build a faster than light vehicle or something else like that. What do you think about whether there would be evolutionary benefits to altruistic behavior on the part of alien civilizations?
Well, altruism is absolutely an essential part of group living. Now, it arises for a whole bunch of reasons. Animals cooperate and help each other for lots of reasons. They cooperate because they're related to each other. They cooperate because perhaps they wouldn't be able to get something done together if they didn't. Sometimes they cooperate just because they have no choice. So cooperation and altruism, loosely defined, is very, very, very common. And it's very common in group living animals.
Mm-hmm.
Now, you can't really, I would postulate, you can't have a technological civilization that's not group living. I just don't believe that you know, you need someone to pass you the screwdriver, basically. So any civilization that we're going to come into contact with is going to be social. It's going to be living communities. I must just recall a joke, in joke from the SETI scientists. A friend of mine in SETI Institute told me, he said, there are two kinds of organisms in the universe: folks and critters. Folks is anyone who knows how to build a radio telescope, and critters is everything else. And the logic behind that is, yes, there may be intelligent organisms, there may be intelligent animals on planets all across the universe. If they can't contact us, we'll never get to know about them. So really what we're talking about here, if you're talking about aliens helping us, it's technological aliens. It's aliens who know how to build a radio telescope, and they've got to live in a group to do that. So they've got to be altruistic within their group. Now the question is, are they going to be nice to us, or are they going to be nasty to us? And this is also a science fiction trope. And my opinions on this are quite firm. That I think they will be nice to us, and I think that, well, there's two reasons really. One is that if you look at the way that we're going, you look at the way things are going on Earth, it's not looking good. It's not looking good for us. It's not at all clear the human race is going to be able to survive much longer, and this may actually be the way that technological civilizations end throughout the galaxy. It may be very, very common. But a technological civilization that can get through this phase, that can solve its climate crisis, that can stop wars and poverty and so on, if it can get past that stage, then they may be able to contact us. But then they're presumably already, they're not into colonization. They're not into coming and eating us. You know, they've got past that stage. So that's what I'm very much hoping for.
Great. Well, you know, what you just described is exactly what was in a paper that Sebastian von Horner wrote in the early 1970s about what civilizations have to get through and why we likely will not get much in the way of contacts. They've moved beyond that stage. I wanted to move to a topic that may be of interest to people in terms of organisms, dolphins. And I know that they are near and dear to your heart as well. And in a section of the book, I'm going to just read from it quickly. This was in the section about whether or not dolphins can evolve, right? And you said, are the intelligent but not quite linguistic species of today, like great apes and dolphins, simply waiting in the wings to step into our shoes when we are gone? And you make an argument that that's not likely with dolphins. And I wonder if you would say, explain why that's not likely. Again, because there are science fiction authors who have made sure that there are intelligent dolphins.
Yeah. Well, so clearly dolphins are very, very well adapted to the niche that they live in, right? That's the way that they've evolved. That's the way they need to be. They are extremely intelligent. They are very communicative. They've got very complex communication. They don't have a language. As far as we know, and this is one of the things I work on, they don't have a language. Now, we don't exactly know why humans evolved a language, but we've got a pretty good idea that it's to do with the complexity of our social groups. That the more complex the social groups, the more complex the communication, and eventually you get to a level of social complexity where we just got pushed over the edge to the kind of language where we can express an infinite number of concepts. Now, dolphins live in fairly complex communities, but not communities as complex as early proto-humans lived in, and nor is it likely that they would need to. One of the things that drove humans, of course, to live in larger groups and to change their ecology was the changing climate and the jungles being converted to savannas and so on. And so the challenges facing them changed. Could this happen in a marine environment? It could, given the right conditions, but there's nothing going on at the moment that would be pushing dolphins to have this more complex social structure, and therefore more complex communication.
Okay. So we can't hope for that without maybe intervention, which is what some of the science fiction.
Oops, yeah. What could possibly go wrong, right?
There's all sorts. Well, you know, we promised that we would give time for some questions here. Yeah. So I think we should go on. Benjamin, you've been monitoring the Q&A. Are there some things in there that you think we should bring up right now?
So there definitely are. We've gotten quite a few questions. I'm going to start with this one, just because I think a couple askers have asked it in various different ways, but I'll go with the one that's most succinctly put. So an attendee asks, why must Darwin's theory of evolution apply to non-human beings? I know you talked about it a little bit, but if you're able to sort of answer it, you know, in that way.
Yeah, it's not that easy to answer. I presume by non-human you mean non-Earth beings, because obviously evolution acted on all life on Earth. So there's kind of two answers. The bad answer is we don't know any other way the complexity can accumulate. And that's not a great answer. But the trouble is, it's actually kind of true. You know, think. There's no way that complexity can just sort of like spontaneously come together and become more and more and more complex. A slightly better answer is that evolution by natural selection is actually very, very common. It's something that's mathematically defined. So as long as the necessary conditions, which are very simple conditions, very few things needed, if those conditions are present, evolution by natural selection will take place. It will take place on everything. It doesn't just take place on life, you know, it happens on computer programs. It happens on religions and internet memes and things like that. So this is a very fundamental process in the universe, and so you would expect it to occur wherever those conditions are met.
And then I'm going to jump to this question, which is a little bit sort of about, I guess this person was sort of thinking about the architecture of life. So much of science fiction is full of creatures who, though impossible in a terrestrial sense, still function like terrestrial animals, e.g. the spider-like creature from Mars still moves in a familiar way. Does this tendency to create organisms that still resemble our own align with your thesis that across space, evolution will always inhabit the same architecture?
To some extent, yes. But of course, to a large extent, no. So there are constraints. The constraints, like I've talked about, constraints of mechanics and constraints of interactions between individuals. But life on Earth has evolved the way it has because of a set of coincidences. Okay, we have four limbs just because the fish that we evolved from had 4 limbs, right? And it didn't need to have 4, could have had 16. So there's a lot of coincidences along the way. So we can't expect life to be quite like what we have on Earth, but there are things that will be in common. So for instance, symmetrical, even number of limbs is something that we could expect if we're going to expect animals to be symmetrical. And again, it's a question of similar solutions to similar problems. So although we can't be sure that any particular alien planet will have spiders on it, we can be quite confident that somewhere in the galaxy there's a planet with something like spiders on it, because there just aren't that many ways of walking around.
So I'm going to I'm going to jump around a little bit. I'm going to jump to this next question that just came in because I think it's interesting. So attendee asks, what about language and communication? Is there an inevitability to the way that communication develops even amongst species on other planets?
We think there is. This is active research, so this is not clear at all. But when you look at communication in animals and the difference between communication and language and which animals have what, you notice a lot of statistical trends. Now, there's no reason for these two. This has nothing to do with it being planet Earth, right? They didn't inherit these tendencies to communicate in particular ways, because very often these animals don't share a recent or a communicating common ancestor. So we do see patterns in communication, particularly patterns of efficiency. So the way that information is organized in communication has particular statistical patterns that seem to imply that it's been shaped to be efficient. And that's a pretty strong indication that this is something that we'd find on other planets as well. Yeah.
And then pivoting to this question, it's a little bit about constraints as well. So an attendee asked, is it possible that, assuming that extraterrestrial life exists, it's been restricted to single-celled organisms and simply will never make the leap to anything more complex?
Yeah. Well, yes. And you know, it kind of might be a bit disappointing if the only alien life we find is that green slime. But remember, Earth, it took a long time for multicellular life to arise, right? It took a very long time. Now, the Earth is a relatively young planet, but you've got to remember the universe as a whole is only 14.5 billion years old, right? And Earth is 4.5 billion years old. So we're not talking about infinite amounts of time around that in which all these things could evolve. So yes, I imagine that on a lot of planets, there will not be that leap to multicellular life. We don't really know what caused life to become multicellular on Earth. But on the other hand, there are experiments people are doing at the moment which seem to show that multicellularity is actually quite an easy thing to evolve, that it probably could evolve under lots of different circumstances. So I actually think there will be multicellular life elsewhere in the galaxy, but it needn't must be.
Another inevitability question next, and then I'll try not to throw too many of them at you. But is it inevitable for extraterrestrial life to be made of the same organic compounds as life on Earth, or is there variation? Well,
I think that there's general consensus that organic carbon chemistry is probably what all life is going to be based on. Whatever science fiction will tell you, there doesn't seem to be any realistic possibility of silicon-based life forms or anything like that. And again, coming back to what I said earlier, you've got to remember, these organic compounds are really, really common. They're everywhere. So they're very reactive. They'll do all the interesting things that life does, and they're very common. I think we can be fairly confident that that's going to be very common. We can't be confident that life will be based on something like DNA. Now, we don't know to what extent DNA is the only way of doing things, or to what extent it's just one of many ways. Almost certainly it's one of many ways. So I think that the fundamental biochemistry will be quite varied, but I think it will be organic chemistry. But there's one thing that I have to say, that I have to say this every time. There will be cases where I am completely wrong. I have no doubt about that. There will be instances where I will be everything I say is utterly wrong. But those instances are going to be rare, right? There may be the odd planet or two that's got some other kind of weird chemistry on it, but the vast majority of life is going to conform to these rules.
Great, thank you for filling in those gaps for us. I'm going to end with this question, which I think just touches upon maybe what a lot of us in the audience think of when we think of aliens and what we've been introduced when it comes to aliens. So This attendee asks, what are your thoughts on science fiction and how it has shaped our understanding of extraterrestrial life? Is there a value to sci-fi and its imaginative reaches, or do you think it hinders our vision a little bit?
So I like sci-fi, and as I said, it's got roles apart from telling us about alien life. The nature of science fiction has changed a lot. You know, it wasn't that long ago. Well, it was quite a long time ago, you know, hundreds of years ago, that alien life was totally acceptable, right? Everyone believed in angels and stuff like that. And this was just no big deal. And then rationalism came along and we tried to fit it into what we understood. And as in the like second half of the 20th century, people didn't find we didn't find any alien life, and so there was this huge skepticism, and science fiction was viewed as being purely entertainment, and so it played up to that, you know, a lot of it played up to that role of being purely entertaining and not particularly probing the possibilities. Now the other thing that happened in the second half of the 20th century that was disastrous for our understanding of alien life was the Cold War, because science fiction then just basically took up all the tropes of the Cold War, and the commies are coming to get us, the aliens are coming to get us, and that's really shaped a lot of how people think about aliens now, is they're coming to get us. But that was just really that one period in history. I mean, there's War of the Worlds, I suppose, but there've always been people coming to get us. But yeah, the alien as the disguised human aggressor is a very unhelpful element of science fiction. But I think there's been so much fantastic science fiction that really has challenged us and helped us to think in much more imaginative ways, for me anyway.
Yeah, the element of foreignness, I feel like, is often the ways that we interpret aliens, you know, and all the different ways that foreignness can inhabit. So that was our final question, and we are at the hour. But before I end things, I just want to sort of say any final words from either you or Lewis before we sign off for the evening.
I just want to thank Arik, and I wanted to thank Benjamin and the Harvard Bookstore for this opportunity. I've really enjoyed it, and I'm looking forward to Arik's next book,
which will be about animal communication. Yes.
Wonderful. We look forward to it. Great. Well, thank you once again to Arik and Lewis for this fantastic conversation. Thanks to all of you out there for spending part of your evening with us. Please learn more about this book and purchase your copy of The Zoologist Guide to the Galaxy at harvard.com. I've put the link in the chat a couple times. On behalf of Harvard Bookstore, the Harvard Division of Science, and the Harvard Library, all here in Cambridge, Massachusetts, enjoy the rest of your day, keep reading, and be well. Thank you both again for joining us this evening.
Thank you.
Thanks a lot.
Have a good night.
Bye.